Hello, my name is Taewoong. Today, in this video, I'd like to talk about perceptually optimized sound zones. This was presented at ICASSP 2019 and a joint work between me, Jesper Kjær Nielsen, and Mads Græsbøll Christensen. Let's begin this presentation with a simple example. Suppose you are with your friend now and you're gonna watch a movie together. You want to watch that movie with English and your friend is with Danish. What will happen if you just play the movie? It will end up like this.
Hvad siger du? Altså, fordi han er et dovendyr, så kan han ikke være hurtig. Jeg troede, at alle i Zootopia skulle være lige, hvad de vil.
Two languages are mixed up, so this is not what you expect. In sound zone control, what we are trying to do is using many loudspeakers to create different listening areas for different audio contents. So in this example, we try to create a zone for English speech and also a zone for Danish speech at the same time. It has been reported that the contrast between these two listening areas is about 15 dB, which means that the interferences are still audible. We know that we need more than 15 dB of contrast to satisfy people inside a zone. If we add more loudspeakers, it might be able to have higher number of contrast, but here in this presentation and in this work, we try to do something else that makes 15 dB of contrast more than enough. This is inspired by perceptual audio coding, and it has been shown almost 3 decades ago through a 13 dB miracle demonstration. So in this slide, there are two audio examples. On the left-hand side, this is where the current sound zone control is, and on the right-hand side, this is what we are pursuing. They have the same level of contrast, but on the right-hand side is only improved perceptually. To exaggerate this effect and this idea, one speech and one white noise are introduced.
Well, are you saying that because he's a sloth he can't be fast? I thought in Zootopia anyone could be anything. Well, are you saying that because he's a sloth he can't be fast? I thought in Zootopia anyone could be anything.
Here, we don't try to improve the contrast itself. Instead, we try to shape the interference so that it becomes less audible or ideally inaudible as in perceptual audio coding. So the next question is that can 13 dB miracle for sound zones be possible? In order to answer this question, first we'd like to introduce mathematical descriptions for sound zones. As you can see from this figure, we have L loudspeakers. An input signal xn, n is time index, is fed into all loudspeakers with FR filters. And these FR filters are what we are going to design. Each of the zone is specially sampled by M microphones or M control points. For an input signal, sound zone control tries to create a bright zone whose sound pressure level is as high as possible and a dark zone whose sound pressure level is as low as possible at the same time. Doing this for another input signal the other way around, and we superpose them together, finally we can have multiple bright zones. Then now we can model reproduce sound pressure at control point M by using a linear convolution between input signal, room impulse response function, and control filter. And this part can succinctly be described by using vector notation. And also, for L different loudspeakers, we also can stack this YML together. Then we end up having this YM vector and Q vector. This YM vector is uncontrolled sound pressure and Q is the control filter. Now we also can define the desired sound pressure at control point M. Typically, the desired sound field for the bright zone is part of the sound field generated by a virtual source, Z. So that's why we have these expressions for the control points in the bright zone. But nothing is desired in the dark zone, so that So that's why we have 0 in the dark zone here. Now we can define the difference between the desired and reproduction pressures by using this expression. In general, we also can introduce a weighting filter Wm, then we can have a weighted reproduction error. So in this presentation, this tilde notation shows that the quantity is a weighted quantity. This weighting filter Wm is the key factor for creation of perceptually optimized sound zones, so we need to have a look how to get this weighting filter. We have used the psychoacoustic model to calculate the masking curve from the given input signal. This is one example. So from the given input signal, we also can calculate pulse spectrum. And by using this pulse spectrum, we can calculate masking curve. So in this frequency range where the masker has higher power, then we allow for bigger reproduction errors in this area. On the other hand, we penalize errors where the masker has less or no power. By inverting this curve, then eventually we can have the weighting filter. In this way, we can perceptually shape the reproduction errors. Then the next question is what will be and how to define the masker. In this work, we have two zones. We label them zone alpha and zone beta. We're going to generate two bright zones. That means we have two audio inputs, XM alpha and XM beta. And zone alpha and zone beta are going to be the bright zones for XM alpha and XM beta respectively. For XM alpha, because zone alpha is going to be the bright zone for XM alpha, that means the masker is going to be DM alpha. For zone beta, it is going to be the dark zone for XM alpha, but eventually this is the bright zone for XM beta. That means the masker is going to be the DM beta. We can do the same thing for XM beta as well. Zone beta is going to be the bright zone for XM beta. That means the masker is DM beta. For zone alpha, it's the dark zone for XM beta, but eventually the masker is DM alpha. From this observation, we can see that the masker is not depending on the signal we are interested in, but it depends on the zone itself. Now we know how to get this weighting filter Wm. So in this weighted reproduction error, you know everything. Now we can measure the distance between these two terms. This can be done by calculating reproduction error for each of the zones. For the bright zone, we can calculate signal distortion power, which describes how much distortion is present. This is spatially and temporally averaged norm to scale value. And in the same manner, we also calculate residual error power for the dark zone, which describes how much power is remained there. And by minimizing this signal distortion power with a constraint regarding residual error power, it allows us to have objective function with a parameter mu, and this mu controls the relative importance between signal distortion power and residual error power. This Q is what we're going to design, and we solve this objective function with respect to Q, then it ends up ACCPM solution in the time domain if no weighting filter is considered. Now we can do something further by exploiting some properties of these two matrices. These are real, symmetric, at least semi-positive definite matrices, and this allows us to compute the joint diagonalization of these two matrices by using their eigenvalue and eigenvector matrices. If we sort eigenvalues in a descending order, then the most important information will be represented in the first or a few first eigenvector and eigenvalues. That allows us to use a low-rank approximation of these two matrices. Then where do we use this? We can use this to design control filter Q. And Q is a linear combination of eigenvectors. That means U is a basis function for this Q, and the only unknown is this coefficient vector A. If we plug this Q into signal dissolution power and residual error power, then we can get these two equations with respect to A. Now doing a V-rank approximation sense, which use the first eigenvectors, then we also can approximate Q with respect to UV and AV. Then now we optimize over AV instead of this Q directly. Then now we can rewrite the combined objective function with respect to UV and AV. And from here, because UV is known and AV is unknown, so we can solve this with respect to AV, and it allows us to have the optimal coefficient vector, which is given by this expression. And finally, we plug this into Q, then we can have this closed form of control filter solution. Except for V and mu, all values are known, so that means these V and mu are user parameters that user can choose. And actually, these two user parameters will give us a very flexible framework. And now let's see how flexible this framework is. Let us assume the weighting filter is the chronicle data function. Then this framework will give us the many existing methods as special cases. For example, if we choose the first eigenvector which corresponds to the largest eigenvalue, then it will give us the ACC in the time domain solution. It guarantees the maximum acoustic contrast, but at the same time, it also gives us maximum signal dissolution. And if we use all eigenvector and we set mu is equal to 1, it will be pressure matching solution. This gives us very small acoustic contrast, but also it guarantees very small signal dissolution. Interestingly, these are the boundaries for signal dissolution and acoustic contrast. So by tuning this V and mu, the user can have very various control filters depending on their preference. So for example, if you use all eigenvectors, then that's ACCPM in the time domain solution. And when on top of that, when mu is equal to 0, then that's MVDA solution. And depending on V and mu, that's variable span winner, variable span minimum dissolution filters. To evaluate and also compare the existing methods with the proposed method, we introduced 5 evaluation metrics. 3 of them are physical metrics, which are acoustic contrast, signal dissolution power, and target to interferer ratio. Besides, we also have perceptual metrics such as TOE and PASC. The performance can be seen from these figures. These green curves shows the performance from ACC, and blue curves are from PM, and these red curves from our proposed method, PBEST. Here solid curves are for zone alpha, and the dashed curves are for zone beta, but they have the same tendency. So ACC will give us the maximum acoustic contrast, but at the same time, it also gives us maximum signal dissolution. And the target to interfere ratio follows the same tendency. On the other hand, pressure matching gives us very small signal dissolution, but at the same time, it gives us very small acoustic contrast. Target to interfere ratio follows the same tendency. This PFAST, our proposed method, it doesn't guarantee the maximum acoustic contrast nor small signal dissolution power. Its performance is in between these two boundaries, but from the perceptual point of view, it outperforms the existing methods. We also conducted various simulations based on the parameters which are shown in this table. For example, 8 loudspeakers were used, and each of the zone was specially sampled by 8 control points each. The location of the virtual source was outside of the loudspeaker array. So now let's hear how it sounds with different methods. The first one is the result we had earlier in this presentation, and the second one is a result by ACC in the time domain. The third one is a result by PM in the time domain, and the final one is a result by our method.
Hvad siger du? Altså, fordi han er dovendyr, så kan han ikke være hurtig. Jeg troede, at alle isotroper skulle være lige, hvad de vil.
Are you saying that because he's a sloth he can't be fast? I thought in Zootopia anyone could be anything.
Are you saying that because he's a sloth he can't be fast? I thought in Zootopia anyone could be anything. Are you saying that because he's a sloth he can't be fast? I thought in Zootopia anyone could be anything.
We also can expect the same tendency for Dennis' example as well. Not only for simulations, but also we conducted A/B preference listening tests to 17 subjects. We had 4 different scenarios, and each of them is speech-speech, music-speech, music-music, and speech-speech. The primers for all these sets were chosen empirically, and you can find the details from our paper. Also, you can hear all the repeater sounds from this following link. And from this result, we can clearly see that P-Vest outperforms PM in terms of perception. In this presentation, we propose a framework for creating perceptually optimized sound zones. This can be done by shaping reproduction error so that it becomes less audible or inaudible to the listeners. This framework trades off acoustic contrast at a cost of reproduction error. We could show how this works and the concept of this approach through the experiments. We could show the proposed method outperforms the existing methods even though we use averaged masking curve here. If we consider segment-wise masking curve, then it might be able to expect the performance improvement later. Thank you for your attention.